All right, so now let me say something about Hamilton's variational principles for Hamiltonian mechanics. Um, so you might know what is called Hamilton's phase-space principle, which says that if you take variations of this sort of action integral, but sort of essentially written in terms of the Hamiltonian, you get pq dot minus h qp dt equals to 0. And then you have to specify the boundary conditions, right? So subject to fixed initial position, q0, and final position, right? Then the stationarity conditions are basically just Hamilton's canonical equations. Okay, so you just get Hamilton's equations, which say that q dot is equal to dh dp, and then p dot is equal to minus dh dq. All right. So, so what we're going to try to do, if you will, is that the same way that the it's like Hamilton's principle plays an important role. It's like in constructing, it's like the exact discrete Lagrangian. We're going to try to find the analog. It's like for the exact discrete Hamiltonian. Okay, so if you will, it's like fixing the initial and final position is consistent with what you would want to do if you have one of these type 1 generating functions where you've prescribed the initial and the final position. Okay, but as we showed before, the appropriate notion or the appropriate type of generating function, it's like for studying Hamiltonian dynamics, isn't the type 1 generating function, but they're the type 2 and type 3 generating functions where you specify the position at one endpoint and the momentum at the other endpoint. Okay, so you might ask then, well, if I were to change the boundary conditions, to the variational principle, does the variational principle change as well? And indeed it does. Okay, so if you wanted to arrive at Hamilton's canonical equations, but where I say prescribe the initial position and the final momentum instead, then I can't take variations of this particular integral, but I have to use some other thing instead. Okay, and the appropriate problem then is given by, so this is, let's say, what we call the type 2 version, right? Type 2 Hamilton's principle. Okay, so what you want to do is you want to take variations of this thing, which is the position, the momentum at the final time, the position at the final time, minus the integral from 0 to the final time of this pq dot minus h qp dt. All right, and you want the whole thing, the variation of the whole thing to be equal to 0. Okay, so and then this is subject to the type 2 type generating function, the type 2 type boundary conditions. So it's subject to fixed q0 and p of t. Okay, so the claim, if you will, is that if you wanted to get Hamilton's canonical equations from a variational principle which prescribes the initial position and the final momentum, then you're not taking variations of this action integral, but you're taking variations of this object instead. Okay, and if you know something about generating functions and Legendre transforms of generating functions, then you can see that this is exactly what you would do if you want to take a Legendre transform which takes a type 1 generating function and gives you a type 2 generating function. So this is the exact thing you would work with. It's like from that basis. Okay, so let's see that this is indeed going to give you what you want. Okay, so let me rewrite this in a corner somewhere, say here, right? So So I want to take the variation of p at the final time, q at the final time, minus the integral from 0 to t of p q dot minus h qp dt equals to 0, subject to fixed q0 and pt. Okay, so that's this type 2 Hamilton's principle, basically. And let's see that this actually gives you Hamilton's canonical equations as the stationarity condition. Okay, all right. So, so you can compute that variation. So the variation of this S, let's call it, okay, is equal to Q at the final time times the variation of P at the final time, right? So this is just the product rule basically applied to this first term, okay, plus P at the final time variation of Q at the final time minus okay, so all right, so let me do that first, and then I take variations of that thing, right? So plus the integral from 0 to t of let me differentiate respect to q first, right? So you just get minus dh dq, right? Variation of q, or minus minus, so that's plus, sorry, plus. Okay, plus there's a p dependence, so the p dependence comes from differentiating this first term. I get a q dot, there's a minus q dot plus dh p, variation of p, right? And then there's a q dot dependence, right? So minus okay, p d q dot, okay, and the whole thing is integrated. All right, then of course you know that what you do is that you take you integrate by parts this term, right? So so that adds a bunch of boundary terms. So you get q of t variation of pt plus pt variation of qt. So this is just from this line. There's a boundary term which comes from the integration by parts now, which is going to be minus pt variation of q at t plus p0 variation of q at 0. And of course these terms cancel out. Okay, so these terms cancel out. And then you are left with a variation of q times p dot, right, with a plus sign. So this is equal to the integral from 0, well, sorry, not equal to, plus the integral from 0 to t of p dot plus dh dq, variation of q, right, plus minus q dot plus dh dp, variation of p dt. All right, then I use the fact that q0 and pt are fixed, which mean that the variations in q0 equals to the variation in pt, which is 0. Okay, so variation in pt vanishes, this disappears. Variation in q0 vanishes, this disappears. So you're just left with this thing now. Okay, so this is just the integral from 0 to t of p dot plus dh dq, variation of q, plus minus q dot plus dh dp, variation of p dt. And by the fundamental theorem of the calculus of variations, right, in order for this thing to vanish, for all possible variations in q and p, right, it has to be that, of course, these things inside the round parentheses vanish. So this implies that p dot is equal to minus dh dq, and q dot is equal to dh dp, which are of course just Hamilton's canonical equations. So what this basically tells you then is that if you want to prescribe initial position and final momentum, then the relevant variational principle is to take variations of this object. And as you might expect, that's going to be the object which we want to approximate when we're trying to construct sort of the exact type 2 generating function. Okay? All right. So okay, so if you're given one of these generating functions, it's like what should you use? It's like to generate a symplectic map. Okay, so if you're given one of these HD pluses, which depend on Q0 and P1, right? Then you can check that the relevant symplectic map generated by this is given by Q1 is equal to D2 HD plus Q0 P1, and P0 is equal to D1 HD plus Q0 P1. Okay, and there's actually an easy way to sort of see how to get at this, and it's based on this observation, if you will, that if you take the exterior derivative twice, then the discrete Hamiltonian has to vanish. Okay. All right, so sorry, if you take the second exterior derivative of the discrete Hamiltonian, it's always 0. Okay, so 0 is equal to d squared hd plus q0 p1, which is equal to, so let's just write down what this is, right? So this is just d of d1 hd plus q0 p1, right? So if I take the exterior derivative with respect to the q0 term, I will get this derivative, this part derivative, dq0 plus d2 hd plus q0 p1 dp1. Okay, and then if you recall, it's like what happens, it's like in the proof of symplecticity is that you want to then write this as being something like the difference of the canonical one forms. Okay, so if you have omega, which is exterior derivative, technically minus the exterior derivative of it's like p dq, for example, right? Then so because omega is just dq wedge dp, for example, right? You can choose different. The point is that you can choose different one forms. It's like which will still give you the same symplectic form. So I can write it as p dq if you prefer, but I can also write this as maybe q dp, right? So if I take d of q dp, it's like then maybe I should put the minus sign here and then some minus sign here, right? So either one of these one forms would work just as well. And if you recall, it's like the basic idea is that you want to identify these partial derivatives. It's like with either p or q in the appropriate sense. So okay, so if you sort of skip a few steps and then you realize what you're trying to get at, what you're trying to get at is that you get d of something like it's like p0 d q0, right? Minus, if you will, q1 dp1. Okay, so this is going to be the difference of two things, it's like which are going to eventually give you the symplectic forms, right, at the different times. Okay, and so the difference of the symplectic forms at the two times, it's like being equal to 0, of course, means that the pullback of the symplectic form by the discrete map is the symplectic form itself, which is to say that the map is symplectic. Okay, so yes, right. Yes, and then it's like what you do is you sort of identify these two things, right? So P0 is D1, right? And then okay, so let me just write it this way, right? So this is this plus this, okay? And that is, of course, just the symplectic form at time 0 minus the symplectic form at time 1, right? Okay, so if you were to just equate P0, it's like to this piece, right, which is paired with the dq0 term, and you pair, so identify D2 HD plus Q0 Q1 with Q1, right? Then you exactly, of course, get these equations. So another way to put it is that one way to see it's like what the appropriate way to generate a symplectic map is from the generating function is to basically assume that the map is symplectic and then sort of, write down the appropriate conditions which guarantee that the pullback of the symplectic form by the symplectic map, well, by the map is actually symplectic, right? Or is the map, the symplectic form itself, okay, which is basically what we're doing here. Okay, so anyway, so this hopefully gives you an idea, it's like, again, of where these kind of conditions come from, okay? All right, so let me just stop here for now.